Hi guys, Mr. Robeson here. We are looking at 6.2 today, solving separable differential equations. So it's differential equations that we can separate. All the x's on one side and all the y's on the other side. All right, so the way I like to think about it is so here's a differential equation. All right, we can't just take the derivative of this side because it has x's and y, or sorry, the integral of this side to get rid of the derivative because it has x's and y's. But what we can do is we can move all the y's to one side. So if we just multiply out this y, we'd have y times y prime equals 2x. And if we want, we can think of it this way. We can think of this as y times dy dx equals 2x. And we can think of just kind of moving the dx up over here. Like that. And now each of these becomes something that we can integrate. So if we integrate this side, we get y squared over 2, technically, plus c. And if we integrate this side, we get 2x squared over 2. So we're just x squared plus some other sort of c. We'll call this maybe c2, and we'll call this one c1. All right, now what we can do, since there's c's on both sides, is we can kind of just maybe move this c over here, subtract c1 from both sides, and we get c3, say. So we could get y squared over 2 equals x squared plus some other c. All right, so c1, c2, c3. All right, and we can say there's our answer right there, or we can solve for y if we want, or we can put x and y on the same side. Like, there's lots of different things we could do. We can multiply everybody by 2 to get rid of the fraction, but this right here is good enough for me right now. This is a general solution, right? Because it still has this plus c here. All right, so that's why this is a general solution. Can we check our answer? Well, we could take the derivative of this implicitly and then try and solve for dy dx. If we took the derivative of this implicitly, so implicit differentiation, we'd get 2y over 2 times dy dx, or y prime, equals, we take the derivative of x squared, we get 2x. Take the derivative of c, we get 0. All right, so the 2's cancel out here, and we can just divide by y, and we get dy dx equals 2x over y, which is what we started with. So yep, that checks out. We can check our answer by implicit differentiation. All right, let's take a look over here. So this is a very special kind of differential equation. So this says the rate of change of y is proportional to y itself. Right? So the rate of change of y is dy dx. Or we could have dy dt, sometimes if we're working with time, is proportional, so that means it's equal to a constant times y, like that. All right, and this is the equation we use for exponential growth. So we can actually solve this differential equation. I'm going to do it with t, just because we usually do it with t. All right, so let's see. I'm going to say it equals ky times dt. I'm going to divide both sides by y, so I get dy over y equals k times dt. And now if we integrate both sides, this one with respect to y, we get the natural log of the absolute value of y. This one we get kt plus, we'll say, c1. All right, notice I didn't even bother writing a c on this side. I just put a c over here. All right, to solve for y here, we take the e of both sides. So we get e to the kt plus c1. Now we use a little trick here. We say this is e to the kt times e to the c1. And then this is some other constant, which we can just call c. So what we end up getting, right, because e raised to just some number is just a constant, is some constant, we'll call c, times e to the kt is equal to y as a function of t. Right? And that's exponential growth. So if we have some sort of amount here, it's usually our initial amount, usually our starting amount, e to some constant times t, and that is how the exponential growth equation works. It's also exponential to k, by the way, just k has to be negative. All right, so let's see if we can solve each of these. So let's see, I can move the dx up over here, and I can move this guy, 3 minus y, down over here. and I get dy over 3 minus y equals dx. And now we can integrate both sides. The x side is probably a little bit easier here. We have to use substitution over here. So du is negative dy. So we have a negative here and a negative here. So we get negative the integral of du over u. So negative natural log of the absolute value of u, or negative ln the absolute value of 3 minus y. Over here, derivative dx, or sorry, the integral of dx is just x plus c. I usually like to put the plus c on the x side, but you can really put it on either side. X plus c. There we go. All right, now we can solve for y. A lot of times we do like to solve for y. If we do that, let's see, we just move the negative to the other side here. So we get ln of 3 minus y equals negative x, say minus c, but I'm just going to say plus c1. It's now just a different c. It's been negative. Now we take the e of both sides. We get the absolute value, or just 3 minus y equals e to the negative x plus c1, which is really just some other c times e to the negative x, like that. Maybe we'll call this c2. All right, we don't really need the absolute value here. We get 3 minus y equals c2 e to the negative x. Technically, this c2 would take care of the absolute value. So we subtract 3 from each side, multiply by negative 1. So we get some other c, c3 with that negative 1 there, e to the negative x plus 3. All right, and there's it solved for y. Sometimes we use it solve for y, sometimes we don't. It's really kind of up to the situation whether we solve for y or not. Over here, again, we want all the x's. So this will be my x side, this will be my y side. So I'd have to divide both sides by y. I'm going to get a y on the bottom. I'm going to divide both sides by 2x. Cancel out that. And I'll end up with dy over y equals 3/2. X squared over x is just x. And I'll move the dx over here. And now I'm integrating. So I get the natural log of the absolute value of y equals 3/2 x squared over 2 plus c, which will be 3/4 x squared plus c equals the ln of y. And now I'm going to do the e of both sides. All right, so that cancels that. We get y equals, and let's see, this c will come out in front as some other c, e to the 3/4 x squared, like that. And there's my answer. All right, oftentimes we do end up with these because we end up with dy over y. All right, so let's try some more examples here. So both of those were general solutions. Now we've got some information. We can probably find some particular solutions. So the rate of change of y, that's dy dx, or dy dt, it looks like, dy dt, is proportional to y. All right, it could say like inversely proportional, and then it would be like 1 over y, or proportional to y squared. You know, it could say a lot of different things. This one says it's proportional to y, so it's times y. So we can solve that. We've actually already solved that. We know if we have dy dt equals k times y, that leads to y equals c times e to the kt. All right, we know that because we did it 2 slides ago. Right, here it is right here. All right, y equals c times e to the kt. All right, now we can use the points to find c and k. All right, so if we plug in 0, we should get 2. So we get 2 equals c e to the 0 times t is 0. So we get c equals 2. All right, c is always the initial amount when we have this exponential growth. All right, so now we've got y equals 2e to the kt. And we've got this other point, 2, 4. So if we plug in 2, we get 4. So we're plugging in 2 for t, so we get 2k up there. Divide both sides by 2. Take the natural log of both sides. That cancels out the e and just leaves us with 2k. And divide by 2. So we get that k equals the ln of 2 over 2. We can write that as a decimal if we want, or we can just leave it and say we get y equals 2 is our c, e to the ln of 2 over 2 times t, like that. This is all in my exponent. And now what is the value of y when t is 5? Well, now we would just plug in 5. So y of 5 would be 2e ln of 2 over 2 times 5. And we could just throw that in our calculator and get some sort of decimal. I'm not going to waste the time to do that, but that's how we would do it. All right, let's try the other one over here. So now we've got a word problem. I know some of you don't really like word problems, but they're not that bad usually. So for exponential decay, the rate of decay is directly proportional to the amount present. So the dy dt is directly proportional to the amount present. Why? Suppose 10 grams of plutonium-239 were released at the Chernobyl nuclear disaster. So at time 0, at the beginning, we had 10 grams. How long will it take to decay 1 gram if the half-life of plutonium-239 is 24,000 years? So that means in 24,000 more years, we'll have half of what we started with. Half of 10 is 5. That's what the half-life means. So there's our 2 points. We do need 2 points. So this equation gives us basically that y equals ce to the kt. We know our c, all right? If we plug in 0, we're going to get c equals 10. So we get y equals 10e to the kt. We use the other point to find k, which since it's decreasing, the k should end up being negative, but we can just leave it as k. So we get that 5 grams equals 10e to the 24,000 k. So we divide by 10. We get 1/2. We take the ln of both sides, like that, and then we divide off the 24,000. All right, the reason this is negative is because ln of 1/2 is a negative number. All right, so that's why this ends up being negative. So k equals the ln of 1/2 over 24,000. ln of 1/2 is also the ln of 1 minus the ln of 2, and the ln of 1 is 0. So we could also say this is negative ln of 2 over 24,000. All right, but now we've got our function, y equals 10e to the negative ln of 2 over 24,000 times t. And now we want to know how long will it take to decay to 1 gram? Well, that's a y. So we'd say 1 equals 10e to the negative ln of 2 over 24,000 t. Divide by 10. Take the natural log of both sides. Multiply by 24,000. Divide by ln of 2. ln of 1/10 times the 24,000 divided by the ln of negative ln of 2. And that's going to be what our t is. We can throw that in our calculator if we want. We can change this to negative ln of 10 if we want. There's a lot of things we can do. But again, it's just throw it in the calculator from here. It's not so bad. It's probably going to be quite a while. Like more than 100,000 years. All right, so there's some separable differential equations with some exponential growth. Seems like we're... Okay, that's it. Yep.